Welcome to this explainer. Look, today we're diving deep under the hood of password hashing to see exactly where cryptography meets code, and honestly, why getting it wrong can be totally catastrophic. Whether you're building a brand new application from scratch or maintaining some massive legacy system, understanding how to actually secure user credentials is arguably one of the most critical responsibilities you have. We're going to look at the math, the hardware, and the exact lines of code you need to keep attackers entirely locked out.
Here's our roadmap for today. We'll quickly cover hashing versus standard encryption, look at the danger of fast hashes, evaluate the 4 recommended algorithms, tackle implementation and safe upgrades, and finally wrap up with avoiding common hashing mistakes. Let's get right into it. All right, Section 1, hashing versus standard encryption. Now, the truly fascinating part of a hash function is that it's strictly a one-way street. Unlike standard encryption, there is absolutely no decryption step in hashing. You put data in, and you get a fixed-length string of complete gibberish out. It's deterministic, meaning the exact same password will always generate the exact same hash, but you literally cannot reverse the math to figure out the original input. Plus, thanks to this thing called the avalanche effect, if you change even a single character, like just capitalizing one letter, the entire resulting hash changes completely. And this is exactly what we want for storing passwords securely. This setup right here brilliantly illustrates why encrypting passwords is, well, incredibly dangerous. If you encrypt passwords, that means a decryption key has to exist somewhere in your application environment. If an attacker manages to compromise your database and your server, which, let's be real, happens all the time, they steal both the encrypted data and the key. It is game over. But thankfully, with hashing, the plain text password never exists anywhere in storage. Verification simply works by taking the password the user types in at login, running it through the exact same hash function, and then just comparing the output to the stored hash. If the hashes match they entered the right password, there's no key for an attacker to steal. Moving right along to Section 2, the danger of fast hashes. Okay, this number should honestly terrify you a bit. A single consumer NVIDIA RTX 4090 GPU can compute about 160 billion SHA-256 hashes every single second. Now, SHA-256 is highly secure for things like verifying file integrity, but its entire purpose is to be incredibly fast. If you use it for passwords, an attacker can exhaust the entire 6 quadrillion key space of an 8-character password in just about 10 hours on a standard gaming computer. And if they rent dedicated cloud infrastructure, that time frame drops to minutes. So, we actually need to flip the usual tech narrative on its head here. In almost every other aspect of software development, faster is better, right? But when it comes to password security, faster is fatal. We actually need intentional slowness, which is a concept known as key stretching. You take a weak, human-chosen password and you stretch it out mathematically so that it becomes incredibly computationally expensive for an attacker to brute force. So what makes a hash actually secure? Well, to act like a turtle against that GPU hair, a solid algorithm needs a few specific properties. First, it absolutely must be slow by design. Second, it needs to be memory hard. GPUs have thousands of cores but very limited memory per core. So by requiring a massive amount of RAM to compute the hash, you essentially cripple those specialized cracking rigs. Third, it needs a configurable cost factor, so you can make the algorithm even slower as hardware naturally improves over the years. And finally, it absolutely must have built-in SOLT support, so developers don't have to manually wire up randomness and risk getting it totally wrong. Let's jump into Section 3, the 4 recommended algorithms. So what are your actual options here? Let's break them down. Argon 2-IDE is the current absolute gold standard. It won the password hashing competition back in 2015, and it's the #1 recommendation from OASP. Next is Bcrypt, which has been battle-tested since 1999 and is basically everywhere. Then we have PBKDF2, which is essentially the go-to compliance choice for government and regulated environments because it's FIPS 140 validated. Finally, Scrypt is a highly memory-hard alternative if Argon 2-IDE just isn't available in your particular framework. Whatever you do, never ever use SHA-256, SHA-512, or MD5. Since Argon 2-ID is the absolute gold standard right now, let's look at how you actually tune it. It uniquely tunes time, memory, and parallelism to offer the absolute best defense. OWASP recommends these minimum tunable parameters to balance the scales: a time cost of 2 iterations, a memory cost of 46 megabytes, and 1 degree of parallelism. This specific balance ensures that while it might take just a fraction of a second for a legitimate user to log in, it becomes overwhelmingly expensive in terms of time and RAM for an attacker trying to compute billions of guesses.
Now, bcrypt is incredibly reliable, and it automatically spits out this beautiful 184-bit salted output. But you gotta be aware of a specific technical quirk. It has a strict 72-byte maximum input limit. If you're encouraging your users to use long, highly secure passphrases, anything beyond 72 bytes might just get silently ignored depending on the implementation. And silent failures? Yeah, those are a developer's worst nightmare. To fix this, modern systems using bcrypt often pre-hash the password with SHA-256 before ever feeding it into bcrypt. But again, if you can, honestly just use Argon2ID.
All right, Section 4, Implementation and Safe Upgrades.
Across pretty much all programming languages, the pattern is basically identical. You use a mature, well-tested library with sensible defaults and let it handle the salt generation silently in the background. In Python, you must pass bytes to the bcrypt library, never raw strings. In Node.js, because these functions are intentionally slow, you have to use asynchronous await. If you use synchronous versions, you're going to block the entire event loop and completely tank your server's performance. In Java Spring Security, bcrypt password encoder with a strength of 12 is your go-to. But the absolute universal rule, no matter the language, never, ever write the hashing logic yourself. So what on earth do you do if you inherit a terrible legacy database full of SHA-256 hashes? Listen, please do not force a mass password reset. It's terrible for the user experience, and honestly, users will just end up picking weaker passwords. Instead, you want to smoothly execute a progressive upgrade sequence. First, intercept the user login and check if their account is flagged with the old algorithm. Next, upon successful login, because remember, they literally just gave you their plaintext password right then, you can take it and rehash it right on the spot with Argon2ID. Then just overwrite the old hash in your database by storing the new hash with its algorithm identifier prefix. Finally, flag the account as upgraded. That way, active users just naturally migrate themselves in the background over time.
Finally, Section 5, Avoiding Common Hashing Mistakes.
These are the glaring red flags you really need to look for in your code reviews. We've talked about fast hashes, but also keep an eye out for using no salt or applying a single static salt to every single user. Watch out for legacy iteration costs too. A bcrypt cost of 5 was perfectly fine in 2008, but it offers literally zero protection against today's hardware. Never silently truncate passwords, never log password parameters in your server error logs. And as a final wrap-up reminder, if you think you somehow invented a clever new way to hash passwords, I promise you haven't. Avoid the cardinal sin of rolling your own crypto. Just stick to the standard libraries. If you ever need to prove your security posture to an auditor, consider these guidelines your absolute holy grail. Everything outside of these specific authoritative NIST and OWASP standards is strictly non-compliant and fundamentally puts your entire application at risk. You must use key stretching. You must use a cryptographically secure pseudo-random number generator for a salt of at least 32 bits. And you absolutely must exclusively use Argon2ID, bcrypt, script, or PBKDF2. Before we wrap up, I want to leave you with a bit of a challenge. Think through your answer to this real-world scenario. You now know exactly how to pull off a seamless progressive upgrade using modern memory-hard algorithms. As you look at your own projects today, ask yourself, is your current codebase a fortress, or is it kind of just waiting for a single GPU to crack it wide open? Take these lessons, review your authentication logic, and make absolutely sure your user's data is truly secure. Thanks so much for joining me on this explainer, and hey, happy coding!